Yes, so welcome. We're now doing some quick session in trying to implement a very basic program. But before I come to this basic program, unfortunately, we have to do something that is more deeply involved, and that's why I sent you this file called basis.jl. JL is a Julia file, and I put this file basis.jl now here on my screen where you can hopefully read it. I cannot enlarge it. I also have my cursor here, which with some delay is visible on the screen. So that's essentially how this program looks like. In general, with the Visual Studio Code is the surface, and you have here the Julia program. On the left-hand side is some stuff from the editor, and here below is the terminal in which you can execute things. You can execute actually by pressing this upper button here. You can execute the current program. I would like to go through this program first, and then we can see what it does, why it's used for. It's called Basis. You can imagine that's the base that we will work into. Basis is the German word for this. So we first use the linear algebra package that contains the Kronecker product that we need to define a spin system. And then we start a function, and I call it basis, and then n spins. You can imagine what n spins means. It's the number of spins that the spin system shall have. And then as we write down complex numbers, I like to include this one, which is I equals the square root of a complex minus 1. And that is then the imaginary part. And then we'll define simply here the Pauli matrices. Maybe you can see that these are the different Pauli matrices. So I can take out one, for example, my, and copy it down here, execute, do it again without the and then you see how it looks like, the matrix. So it's 0, minus I, and 0. I mean, I half instead of I. And that's how the matrix looks like. This is really the IY matrix. So I called it here MIY for matrix IY, or whatever you call this. So, and then I have here this initializations. So I fill up here space for operators. That is n order times n order matrix and times n spins. So this has 3 indices. The first ones are for a 2-spin system, for example, the 4x4 matrix. And the third index, it's on the third dimension, which tells that it is spin 1, spin 2, or spin 3. And so in IU, I have the unity matrix, the identity matrix, the 1, for the different spins. And IX is, of course, if a spin here is 1, then it's I1X, this is 2, it's I2X, etc. And I do this initialization with zeros to the correct size according to the number of spins that we have specified. And then comes this one that's a bit more complicated to look at, but it's essentially, let's say, what does this do here? It cannot do it because I-spins is not defined. I-spins equal n. In the left upper corner, it forms a unity matrix that is of the size of the number of spins that are below the I-spin number. So it's I-spin minus 1. That means I defined I-spins equal 2, so 2 spins, and then the left upper corner is the 1 matrix just for 1 spin. If I define I-spins equals 3, you see what comes out. Then it's a two-spin system that's in the left upper corner. And the same thing I do with the right upper corner. And then well, for example, here this IX for given I spins is the Kronecker product, or I should start here to the right, is the Kronecker product with the, well, with the Pauli matrix, MIX, and then on the right-hand side with ones, and then to the left-hand side with ones, and I called them rechts and links, which is the German for right and left. Sorry for using an unusual language. So we create a matrix that does the Kronecker product, and then in the end, we should get the full matrix. So, for example, I do it now. I copy this part and spins I define to be, let's say, 3. Then I copy it and run it. Then let's see, IX down at 1 looks like this. So with this mathematics, what I did is I have here, you see there are some areas where there are non-zero values. Maybe I should first show the, what can I use? Set maybe, IZ1. And then we can see along the diagonal, we see we have all 1/2. And the upper half is plus 1/2, and the lower half and the diagonal we have minus 1/2. And everything is 0. Just because of numerical issues, it's sometimes negative or positive, but it's 0 in the end. And now for the second spin, which we can simply do like this, we should have a different matrix, still diagonal, but then it's plus, plus, minus, minus, plus, plus, minus, minus along the diagonal, according to spin number 2. And if we do the same thing here for spin 3, then we have plus, minus, plus, minus, plus, minus, plus, minus along the diagonal, as it should be. So with this small little program, we created the basis set for all operators we need. And the product operator, for example, 2 times IX of spin 1 times IZ2 can be written like this, simply as the multiplication. So this is 2I1X I2Z. And then this looks like this. And you see that here in this row, there are elements that are non-zero, and in this row as well. So when we have this little program that gives us the basis, the rest is really straightforward. And this needed some nice programming to figure out how to do it efficiently. That's why I just send it to you, not programmed it myself now. And now we will start with some new file, new Julia file, and actually I will save it as ID ends Mac. Now we first have to packages. So we start with using linear algebra, then using plots we will need later on, and using something for the Fourier transform where this FFTW package is quite okay. So these are libraries that have been produced by others, and we simply include them. Then I quickly go to the basis because of laziness, and I copy here the complex number I. Then it's something like define spin system. And here we include now this basis.jl file. So it's red, and when we compile it, it will be compiled with the rest. And then we say n spins equal, let's say, 1 in the beginning. And then we have, well, to do it explicitly, we have IU, IX, IY, IZ, and then IP, IM, IA, and IB equals basis of n spins. Please be careful to keep this order. So IU is the unity matrix or identity matrix. IX, IY, IZ are clear. IP is I plus, IM is I minus, and IA and IB, of course, is for alpha and beta. So that's straightforward, I would say. Then we have simulation parameters. So there we need to define a dwell time. And I would set this to 0.001. Then we need to define n points, the number of points that the FID shall have, like TD and topspin. And that we say it's set to 32K, which is 32,768. Then we need to initialize arrays. So we will have an FID that we record, and that will be filled with zeros first, and complex float 64, and with the size n points. Of course, our ID will be n points long, and that we need to define now. And then time would be zeros, and this is just real numbers, so we directly can call it endpoints because it's the default in the type. And then we already start with the tough stuff, or with the calculation things. And we look at spin, then cities, Hamiltonians, and the corresponding propagators. So we have to initialize our calculation. So I will call row init, our initial row, our row 0 we used to write in the lecture. And that is simply IZ, and then this construct for spin 1. So this is I1Z. Then we take the Campbell shift Hamiltonian for spin 1, and we can simply write down this is minus 2 times pi times the chemical shift number, give it a value, let's say, whatever, 50 Hertz, and then times IZ for spin 1. That's already the chemical shift Hamiltonian, and Coupling we do not have in a single spin. So let's see. So what we now have to do is define the free evolution Hamiltonian usually, which I like to call H-evo, also called H-drift or whatever name. And this would be, in this case, simply the chemical shift Hamiltonian. But when we further continue, we will add something to it. So that's why I put it here. And then if we have H-evo, we can let the propagator work. And the propagator is U-evo, and this is just matrix exponentiation, so exp, and then it's minus I times the evolution Hamiltonian times 12. So that means for a time period 12, that is the time between 2 points that we will acquire, this will give us the propagator, this e to the minus IHT that we have seen so many times in the lecture. Then we also should define a 90-degree pulse, and this we can define in a perfect way, like an ideal pulse. And I think to not have any complications, we simply do this. And this would be, we can directly write down U90Y, which is a 90-degree Y pulse, or shall become, and that would be matrix exponential now of minus I times 2 pi times, can imagine, IY of spin 1. And now this 2 pi times IY, this is a 360-degree rotation, a 2 pi pulse. And so we simply divide by 4. So we get a rotation of pi half, meaning a 90-degree pulse. That's already everything we need in this 1D pulse sequence. We can now simply do simulating the FID. And what we need, of course, in the rho equals rho init in the beginning, our initial rho. But then we will apply a 90-degree pulse. So we know how to do this. This is the U90Y times rho times U90Y prime. And this U90Y prime simply corresponds to U90 dagger in the lecture. That means it's the adjoint of the matrix. So it can be very easily done in this program. And so what we have here is already the evolution of a 90-degree pulse. So we should be from Z go to X, magnetization. And now we want to record an FID. So what we need to do now is a loop structure for I points 1 to N points. And then first we define the time points. So time of I points equals, actually I do this mistake all the time. I'm sorry, this must be a square bracket. This is now I points minus 1 times 12 time. So it's I points minus 1 because we want to start with 0, with the time 0, and times 12 time means we will record n minus 1. That means 32k minus 1 time points altogether. And now we have the FID. And that's just the trace, if you remember. And that's very nicely, it's just TR of rho times IM, because that's something I did not tell you. We record in NMR usually the operator I minus. This is by definition the operator we record in an experiment. It's an observable there. So IM, and this is of course of spin 1. And this rho times I minus, we simply do this, the trace rho times I minus. And then we need to define it as a global variable now, because we're in this loop. The rho we had beforehand is now again evolving, but this time with the evolution Hamiltonian, or propagator in this case. Then this is the end, kind of. But of course we need to look at things now. So we plot, and what we plot should be the time as the x-axis, and of course the real part of the FID, like in the spectrum. And well, I give some parameters which I think are good. And false. And then we can see already now if I made mistakes. Yeah, so we just try now. What I do now is make this a bit smaller. So let's see. So you see what's happening here. We get something here, but something is wrong, apparently. Line 41. Oh yes, of course. So yes, and that's what we kind of expect. A constant FID. It's a single spin. It has a certain frequency. I mean, if we set the chemical shift value to 0, then we should have a constant line with, and it's down there. I mean, there's the 0.5, I guess. Yeah. So yeah, it does what it should. And now, of course, we can plot rather a spectrum. So let's see what we can do there. So we plot, and the time can be calculated with FFT shift and FFT frequency endpoints 1/12. So we take 1/12 time and calculate all frequency shifts there. This is an inherent function of this FFTW library. And then we take the real part again of FFT shift of FFT FID. So let's see if this one works now. Yeah, and we see a single line at frequency 0. That's the spectrum. And we can, whatever, make it 200. Then we should be at the line 200. But what you see is a strange artifact. This is numerical instability. And that is because we do not consider any relaxation. So what I will introduce now is simply I multiply this here. I mean, the FID when we calculate it times matrix exponentiation here. I mean, not matrix, but an exponential minus, and then I points minus 1, that's the time, times 12, and I divide by T2 time. And now, of course, I need to define it somewhere. So here, T2 time equals, and I found something like 1 second or so, typically fine. And when we calculate now, you see that it looks how it should look like. And you even see in the foot that it resembles the Lorentzian line shape that you would expect. So the single spin is maybe a bit boring. Let's be much more advanced to take now a second spin and see what we need to change now. We don't change anything up here, but we start with the initial rho density. We now have to include the second spin. We want to excite the second spin as well. So we simply take here this IZ for spin 1 plus IZ for spin 2. But then in our evolution Hamiltonian, of course, also got more complicated. So we have now a chemical shift term also for spin 2. and I simply give it a different number, let's say minus 200. And of course, it acts for spin 2. And then we have something called J-coupling, the Hamiltonian for the J-coupling between spin 1 and 2. So we now have a 2 times pi times the J-coupling, so 10 hertz times. And now I think we should simulate really a homonuclear spin system, something that is difficult to do or not possible with the product operator formalism. So we do now something that cannot be done so easily by hand. So we need Ix for spin 1 times Ix for spin 2 plus Iy for spin 1 times Iy for spin 2 plus Iz for spin 1 times Iz for spin 2. So this is the full isotropic Hamiltonian that we have in a homonuclear spin system. And let's see what we get with this. Maybe actually I choose the coupling to be small, something like 3 hertz. And this one, 115. We'll see. Now the evolution Hamiltonian, of course, is the sum of all these, of the chemical shift of the first spin, of the second spin, and the J-coupling. And well, the evolution Hamiltonian then is the same. But with a 90-degree pulse, we now have also to include the second spin. So this is plus Iy for the spin 2. Well, simply because we need to apply that as well. Now we initialize, we excite both spins, and then we look at the FID. But when we start it now, and this can be really funny to see, it's the Fourier transform, we see only one signal there to the right. It's because we also detected here only one spin. So we need to look into that. Of course, we do here the sum of spin 1 plus Im for spin 2. And if we then calculate, we get an error. What did I do? Oh, there's a... So, yeah, then we have both spins. And if you look carefully, you see that they are coupled. We can now have some look at the spectrum. If I take 7 hertz, then you see the coupling, but you already see a tiny little bit of strong coupling of the roof effect. And of course, if I go maybe 15 hertz or so, it will get larger and larger. Let's move them closer together. So that should also change. Like 1, we choose to be at the 0 frequency. Still getting larger, the strong coupling artifact. And now we take minus 50 hertz, the other one. And there you see really nicely this roof effect. It's all included in this calculation. And yeah, so we can nail it down even to be at whatever 20 hertz. It's even stronger. And now if we also set this to 0, then we end up with a single line. As you all know, isochronous spins are identical. So that easy, you can see spin physics really being simulated. And not only this, now I do something, I copy this HJ11 and I make it HD11, meaning I simply change it to the dipolar coupling Hamiltonian, which is 2 times the IZ component minus IXX minus IYY, the two components. And then I set the J coupling to 0. I add here the HT1 to the dipole coupling, and the rest should be the same. And when I do this, then we see a splitting. And the splitting is there, although the two spins are isochronous. That's simply because of the form of the Hamiltonian. If I take them at 450 and minus 450 Hertz again, then you see that they are split. But when you look at the small details, then you also see that the roof effect is inverted. And that's typical for dipolar couplings. I mean, when I put them closer together, this inverted roof effect gets stronger. Or you can also make the coupling, let's say 100 Hertz, and you get such a spectrum. I should not be at 450, let's say 350 Hertz. Yeah. Then you see nicely the roof effect of the two spins that are coupled by 100 Hertz, which for dipolar couplings can easily be reached. And it's now a funny thing, like let's make that minus 100 Hertz. So this one line. See now, the left signal is a distorted doublet, and it should be centered at 100 Hertz. But when you look at it, it's a bit shifted to the left. I specified 100 Hertz coupling, but because of the coupling Hamiltonian, we see a 200 Hertz splitting. That's different to the J coupling. So what happens now if I take this signal on the right-hand side and shift it closer? If you're very careful, you see that the left signal shifts further to the left, tiny little bit. And when we continue, like make this 100 Hertz, well, it shifts very little, but it should shift. Now I see it maybe stronger. The left signal shifted a bit more. This is the opposite of what you find when you look at the J coupling case. In J couplings, you're in the second order limit. The two chemical shifts are closer together than they are in reality. With dipolar couplings, they are more separate instead. Just I tell you, like when we specify 100 Hertz coupling, then it's because of this 2IZ, 2I1Z, I2Z term. There's another 2 in there. And because of that, we see a 200 Hertz splitting, although we specify only a dipolar coupling of 100 Hertz. So it's 2 pi D instead of pi J for the two couplings. So we expect a splitting of 200 Hertz now. However, when we now put them both to 0 frequency, then we see that these two lines here, they are not really 200 Hertz apart. Actually, they are exactly 300 Hertz apart. And that's something you can see when they are isochronous. Then we have an isotropic contribution, and that would be minus XX minus YY minus ZZ. And you can separate this Hamiltonian now. You can write it down differently. You can write down this Hamiltonian of being 3 times ZZ minus the isotropic Hamiltonian. And when you're on resonant for both spins, then the isotropic component will not give any splitting, but then you are with 3 times IZZ left. And that is what you see here. And of course, you can get more fancy. So what I prepared yesterday evening was something, I mean, the very same program. You see here 12 times T2 times the points. Okay, I have here some pulse lengths, which is not really important. I don't use it actually. Then here are all definitions, but then I define operators FM, FP, FZ, FY. which is the sum. Fz is, for example, the sum of I1z plus I2z plus I3z plus I4z, whatever we have. And I did this here recursively. I defined this for an arbitrary spin system, so that I do not need to change everything by hand every time that I change a spin system. Then also I have a loop here which defines the Hamiltonian and so on. And well, that's actually old. This is not needed. And then I have everything written in the Hamiltonian with chemical shifts, Hamiltonian with scalar couplings, and Hamiltonian with dipolar couplings. And I define the evolution Hamiltonian as before. I now have the 90-degree pulse, which I simply define over the operator Fy, which is the sum of all Iy. Oh, the row init is Fz, that is the sum of all initial operators Z. And then, of course, I detect here the trace, and then I use Fm for the sum of all I minuses. Then I do the very same thing that we had here. Just that now, for example, I can here use a number of spins being 6. And I have defined here 6 chemical shifts in this array. I wrote it that it goes up to 10 actually here. And then I have a scalar coupling array. So I defined some coupling constants, 1 Hertz, 7 Hertz. And the dipolar coupling constants are 0 at the moment. It's an array. And when I simulate this, then, well, it writes out the different couplings. And then we get a spectrum. And who can tell me which spectrum this shall assemble? Ethanol, right? So the classic example, you directly see it, 6 spins, and that's simulated like that. And well, now you can, of course, simulate with the real ppm values and what's really going on, and do it for, let's say, different spectrometers for 40 megahertz compared to 400 compared to 1.2 gigahertz spectrometer, for example. And all this can be done quite easily, quite rapidly. It's no big issue, but you need to know the mathematics, of course, behind it. I can show something else, maybe. I prepared another program here. It's similar, but here you see read Bruker wave file. So it reads in a shape file. And I have stored this here. This is the Burbob 180.1 pulse that you can find in the Bruker library and in the shape library of Topspin, in the wave directory of Topspin. And this pulse is the pulse that I participated in optimizing. So let's see. How does this pulse shape look like? If everything goes right, it should appear now. That's the pulse shape, and it's not perfectly done, but here you see the amplitude, and the amplitude here in the center has a boost, which turns out to be quite good for the pulse performance before it goes down again to the right. And down here, very tiny, because I did not adjust the height, is the phase of the pulse. So it's amplitude and phase representation of the pulse shape itself. And what you can do now is simply define here offset terms. In this area here, we have offset terms, and these offset terms define the initial row, but we also define the propagator just for the offset term. And then in addition, we have here the H amplitude and so on. And you see this is the pulse with, if you remember, cos D, that's the cosine in degrees, and the sine in degrees. So this is the pulse phase, which is stored in this phase parameter. And we add here evolution with the offset, and then the pulse shape in addition. And then again, we acquire, we look at what's going on. But actually, we do not acquire an FID. We just look which spin density matrix we have after we applied the pulse. We store this in MX, MY, MZ, magnetization components, and then we can plot all this with respect to offset. We can plot the resulting MX, MY, MZ, as well as the square root of MX plus MY, like what magnetization is in the XY plane. And we can do all this. And yeah, let's simply run it, I think. So let's see what comes out. Interesting. I need to hide this again. And what you see here is the inversion performance. And that's quite nice for this pulse. And it was so good that Wolfgang Bermel even decided to use this pulse instead of the chirp cascade that we usually used. And yeah, so one can also look at other pulses. And I think I have here a nice one, which is not from us, which has a different RF maximum. And when you do this, you get a selective pulse. And that's a so-called reverb pulse that I loaded in. And you can nicely, whatever the width was, 10,000, I think that should still be fine. And then you see more details in the region where it's necessary. And there you see that not all pulses are that nice and flat, but still it's a very good pulse. And what we're currently, since quite some time actually working on is also a different type of pulse shapes. And that is 190 microsecond long and has a maximum amplitude of typically 10,000 hertz. So let's see if this one works. I hope it's still in the same directory. Did not check that. Yeah, I think it works. You just have here 10,000 hertz where we see it. It's an excitation pulse that brings Z magnetization into the XY plane, meaning Z magnetization will become 0. So you see green here is MZ. And in the XY plane, we have MXY. And that is pretty much 1 up there. But the individual X and Y components, they're all over the place here. So this is just a so-called saturation pulse, which starts from Z and brings magnetization in the XY plane. And well, if you now look at the width of this pulse, so we would like to cover maybe 50 kilohertz for carbon, also at higher fields, then we see up here this violet line still over the bandwidth of 50 kilohertz nicely covers the whole bandwidth. So it's really nice. But actually, how far does it go? When you look at it here, then you see it's pretty much 200 kilohertz it covers. And 200 kilohertz with a pulse that's only 190 microsecond long. This is enormous. And so we're looking how to do spectroscopy with such saturation pulses, and that's quite nice. You can actually do 2D experiments with this as well. You don't always have a phasable spectrum, but a magnitude calculation you can always do. And it really covers bandwidths that even go far beyond this 200 kilohertz. So we can even do megahertz excitation with this. And so nuclei like whole phosphorus or fluorine with 200 kilohertz already, you get the whole fluorine region. Or platinum, which is notoriously wide. I think platinum on a 600 megahertz spectrometer covers something like 2 megahertz, and that's within reach with this. I think there you run into other problems. That is that your filter width is smaller than 2 megahertz. So the spectrometer would need an upgrade as well than to do this spectroscopy, but let's say up to 1 megahertz is still feasible. These are just some developments I wanted to show you. All this you can also get with Bruker with a shape tool display, as you may know. It's equivalent. Are there any questions? Somewhere around 30 something spins. then you already need 1 gigabyte of main memory to just store this matrix. So then the only way of doing it, and that's why Ilya Kuprov, for example, is able to even simulate 200 spins, is by using this Krylov subspace restrictions. So you say small elements in this matrix, you simply set them to 0, and then you take sparse matrix approaches to do it. But then even with all this, I mean, the calculation is slow. So today, with all these tricks, you are able to calculate, let's say, 200 spins, but it's up to you on how long you are willing to wait for the calculation to conclude. So what we are trying always is to keep the spin system as small as possible, because we are more interested in the properties of the pulses and pulse sequences. So when you can go to the Bloch equation to a single spin, then we do it. Yeah. And then you calculate much faster. You can usually get everything in the level 1 or level 2 cache memory of your processor, which is ultra fast. And then you really can do very quick and very fast calculations. Okay, I think then we should go for lunch.